Review for the third section of our course on hypothesis testing and confidence intervals. I'll start out by going over some of the terminology of hypothesis testing. And this following is a diagram showing 4 possible outcomes of hypothesis testing. By the way, the hypothesis testing, typically you're trying to, you have some data from a sample of a few hundred or a few thousand people, and you want to test hypotheses about what it says about the population. For example, in a sample, maybe a new drug shows a higher cure rate than the old drug, but it could have happened just by chance. So we want to know whether how strong the evidence is that the new drug is actually better than the old. So in hypotheses, you have two, usually you're looking at two hypotheses. Either the null hypothesis H naught, for example, the new drug is no better than the old drug, versus alternative. The alternative is what you're trying to prove. For example, the new drug is better than the old drug. So it's a H naught, the null hypothesis, versus the alternative HA. And so either H naught is true or HA is true, and either we don't reject H naught or we reject H naught. So there's 4 possibilities. There's 2 ways that we could draw a correct conclusion, and there's 2 ways that we draw an incorrect conclusion. It might be that H naught is true and we don't reject H naught. And the probability in symbols is usually expressed as 1 minus the Greek letter alpha, 1 minus alpha, and that's also called the confidence level. H naught can be true and we reject H naught. That's a type 1 error, and its probability is usually designated by alpha. Typically, in hypothesis testing, the experimenter will establish the desired level of doubt or desired probability of a type 1 error. So this is actually the maximum desired probability of a type 1 error. I like to call it the level of doubt. The more common term is level of significance. But anyway, so alpha is the probability of making a type 1 error, which would be rejecting H naught when really H naught is true. Another possibility would be that HA might be true and we don't reject H naught. That's a type 2 error, and that's usually represented by the Greek letter beta. Usually we don't know, we don't compute beta, or we don't know what beta is. In order to compute beta, you need a specific value of for example, the population proportion. If HA is true, you need a specific value to plug in. So anyway, beta is the probability of type 2 error. The 4th possibility that can happen is we reject H naught and HA is true. That in symbols, the probability is 1 minus beta. And that's called the power of the test. Okay, so that's the sort of the basic terminology. The p-value is the actual probability of a type 1 error. So alpha is usually established by the experimenter. That's sort of the maximum desired level of type 1 error. And then the p-value is actually the computed probability of a type 1 error. I have a chart here for interpreting p-values. That was, if you have a p-value between 0.1 and 1, that would be the sample provides little or no evidence for rejecting H naught. Between 0.05 and 0.1, there's some evidence for rejecting H naught, and so forth. So the smaller the p-value is, the stronger the evidence will be. Okay, so we have some formulas. I'll get into this will be a little bit more clear when I get into specific examples. But anyway, these are the formulas that we have been working with. We have the formulas for the testing the population, testing a proportion, and we can apply this formula if NP and NQ are at least 5. N would be the sample size, P would be the proportion of the population with a characteristic, and Q would be the proportion without that characteristic. For example, the proportion cured versus the P would be the proportion cured, and Q the proportion that were not cured. If we don't know, usually we don't know P, so you'd have to put in a P hat here. We usually only know the sample proportion, if you have a P0, if you're comparing it to another population, P0 might be the proportion cured by the old drug. You can put a P0 in here. So in this equation here, I just put a P, but it could be use whatever value you have. If you don't know P, you can put in a P0 or a P hat. This is so these are so we basically have three methods. We have a confidence interval. That's one formula we're working with. Then we have the critical value method. The critical value method doesn't tell you as much, but it's usually less computation. And then we have the p-value. We also have I could do a left tail and a right tail test, but I'll get into these more detail in these formulas. Get into some more details of these formulas. And I think I'm okay. So here's we could also test hypotheses about the mean. We have some more formulas here, and this is see, we have formulas for testing the variance or standard deviation. That's these pages here, for paired data, it's basically the same formula as this is testing whether you have a difference between two means. But if the data is paired, it's basically the same formula as a test for the mean. It's just what you do is you subtract the values. For example, if you have a paired data example, that might be cholesterol levels before and after 6 weeks of a vegetarian diet, to see if that had an impact on the cholesterol levels. So for each person you have 2 cholesterol levels before and after, and you want to find the mean difference, and you want to test whether the mean difference is 0 or not. And then there's also McNamara's test for it's also for matched pairs. If you have patients that are paired by age and clinical condition, one person of each pair is given treatment A, the other treatment B, and we have a formula for determining whether there's a difference between the two patients, two treatments. And then we have formulas for testing whether there's a difference between of means between independent samples. For example, if you wanted to test whether the carbon monoxide levels were different in smoking versus non-smoking areas, you would have a sample of smoking areas, a sample of non-smoking areas, and so we have some formula for that for testing those. And you can also test whether the variances are different, and have a test whether two proportions are different. You might have testing a new drug on patients. One group of patients has moderate symptoms, the other group of patients has severe symptoms, and you want to know whether there's a difference between the proportion cured for under those conditions. Okay, so let's get into some more specific examples. So this is this will use some of these formulas here that I just showed you on briefly showed you, but I think getting into specific examples will sort of help you understand it a little bit better. So example 1, in a random sample of n equals 40 patients, the mean creatine level X bar is 1.3 milligrams per deciliter. Population mean creatine level is unknown, the population of these patients, but the standard deviation is sigma is 0.5 milligrams per deciliter. We want to compare it to the general population, where the mean creatine level is 1.0 milligrams per deciliter, and we want to test this with 95% confidence or 5% doubt. So in symbols, we're testing H naught mu equal 1.0 milligrams per deciliter. Patient creatine level is the same as that of the general population, versus the alternative HA mu is not equal to 1.0 milligrams per deciliter. Creatine level is different than that of the general population. Here we're going to use the Z table here. We'll use the testing a mean and see if I can pull up that formula here. So this is the formula. These are the formulas if the mean is known, and we have a two-sided test here. We have a not equal to symbol here, and the mean is known. The standard deviation is known. We want to test the mean, so we want to use these formulas here, and we'll start out with the confidence interval method. We have three methods here: the confidence interval, the critical value method, and the p-value method. So we'll start out with the confidence level method. So the first thing we want to do is find the z-score. We need to look this up in the table. So anyway, our confidence level is 95%, or as a decimal is 0.95, and if we divide that by 2, 0.475, and then we go to the z-table, and we look that up in the z-table using the z-table in reverse. So we're looking for 4750 in the body of the z-table. If I can find the z-table here. So we're looking for 4750. We're using the table in reverse. 4750 is right here, and it's row 1.9, column 6. So the z-score is 1.96. And then we can compute the margin of error. That's part of the formula here. We have what part of the formula that comes after the plus or minus is the margin of error. So it's the number from the z-table times standard deviation divided by the square root of n. So this is going to be 1.96. Standard deviation is 0.5, and n is 40. So it's 1.96 times 0.5 divided by square root of 40. So we can do that on a calculator. 1.96 times 0.5 divided by second square root 40 equals, and that's 0.15 something. 495 1605, or I'll say approximately 0.15. That's milligram per deciliter. Okay, so so that's sometimes computed separately. I'm going to store that in memory on the calculator here, and then so this part here is the margin of error. That's what was computed, and if we x bar minus that margin of error is going to give us the lower bound. X bar plus that will give us the upper bound. So we do x bar is 1.3 minus the margin of error, and it's 1.3 minus second recall. Get 1.14 something. 1.145 048 395, or let's say approximately 1.145 milligrams per deciliter. And if we add the margin of error to that, we'll get 1.454951605, or approximately 1.355 milligrams per deciliter. Oh, actually 455. 1.3. Yeah, it should be 4. I'm trying to do it in my head and I made a mistake. Okay, 1.455 milligram per deciliter. So that means we are 95% confident that the mean creatine level of patients is between 1.45 and 1.145 and 1.455 milligram per deciliter. And because so we know the sample was 1.3, but that the 1.3 might have happened by chance. But so what it tells us about the population mean is that we're pretty sure the population mean is somewhere between 1.145 and 1.455, and because 1.0 is not between those two levels, then we can reject H naught with 95% confidence and conclude that the mean creatine level of such patients is different than that of the general population. Okay. Now, okay, so the methods 1 and 3 give you more information than method 2. But if you just want to know whether or not to reject H naught, usually method 2 is less computation. It's called the critical value method. It's this second formula here. And some parts of it are going to be the same. The 1 minus alpha over 2, that part of it is the same. It's 0.95 over 2, 0.475. And so that means that Z, again, Z, if you look that up in the table, again, Z is going to be 1.96. That 1.45750 is in row 1.9, column 6. the standard error, we didn't compute the standard error by itself separately last time, but standard error is sigma divided by square root of n. So sigma divided by square. So sigma is 0.5, n is 40. So it's sigma divided by square root of 40. And 0.5 divided by second square root of 40. 0.09. 0.079. 0.56942. Okay, so I'll store that in memory. Okay, so the test statistic is actually a z-score. If you're looking at the formula, this square root of n, if you have a fraction in the denominator, you can put I simplified this by putting the square root of n on top, but basically this is a z-score. It's score minus the mean divided by the standard deviation. So this is the standard deviation of x bar, which has a lower standard deviation than the original standard deviation. But anyway, so this is z-score. Score minus the mean divided by the standard deviation. So 1.3 minus 1.0 divided by the 0.079 something. So it's 3.79 something. Okay. So let's say approximately 3.79. Okay, so so that's our test statistic, and so this number here is our test statistic. The two numbers at end are the critical values, and our test statistic of 3.79 is not between the two critical values of negative 1.96 and 1.96. So again, we reject H0 with 95% confidence, include the mean creatine level of such patients as different than that of the general population. Okay. Okay, so the modern researchers tend to favor the p-value method. The older research, oftentimes the p-value is difficult to compute. For this particular problem, it's not so hard to compute, but for some problems, the p-value method is a lot of computation, and so the older researchers, 100 years ago, before there were computers, favored the critical value method because that's the method with the least amount of computation. But modern researchers have access to computers, and they favor the p-value method. The p-value actually tells you a little bit more than the critical value method. It tells you the probability of a type 1 error. So that's a little bit more information. So anyway, some of it's still going to be the same. The 1 minus alpha over 2, again, is 0.95 over 2, 0.475. And if we look that up in the z table, we get z is 1.96. And the standard error, same as it was before, it's sigma over square root of n. So it's 0.5 over square root of 40. Same as before. That was 0.079 something. 5, 6, 9, 4, 2. And then test statistics, same as we had before. It's 1.3 minus 1.0, push equals, divide by the standard error, and that's going to be 3.79, 4, 3, 3, 9, 2, or approximately 3.79. I for this particular test statistic, because the z-table usually only has z-scores to the nearest hundredth, I just usually round to the nearest hundredth. If you're using the t-test, usually a t-table can carry more digits, so I might carry another one or two extra digits if we're using the t-test. But this, the z-table, our table itself only has 2 digits past the decimal. Okay, so the p-value is going to be 2 times 0.5 minus the probability that z is between 3.7, between 0 and 3.79. So we want to look in row 3.7, column 9 of the table. Actually, the table in our book doesn't, I think, doesn't go up that high. Let's see if I can find the one in the course files. If I can find. I'll just use the table of the book. I think the table of the book goes up a little bit higher than that, but we'll use the one. Now, the table in the book, there's no, a table doesn't go up that high, so it's going to be, the z-score is going to be more than 0.4998, because the highest number on a table is in row 3.4, column 9, so it's going to be more than 0.4998, and so that means when we plug into this formula, this is going to be it's going to be less than 2 times 0.5 minus 0.4998. And that's, so it's going to be less than 0.0004. After you use the table of the course files, actually, in fact, it's actually you find it's even less than 0.0002. Well, it's about 0.002. Our table doesn't go up that high, so we can just, using the table in the book, the most we can say is less than 0.004. But either way, it's a very small p-value, and it's less than our maximum desired doubt, which is 0.05. So again, we can reject H0 with 95% confidence, include the mean creatine level is different than that of the general population. And we can actually say a little bit more. So that is sort of the advantage of the p-value method. Our p-value, if it's less than 0.000, it's certainly going to be less than 0.001. So that our sample provides very strong evidence that the mean creatine level of these patients is different than that of the general population. Part B, if the actual patient population mean creatine level is 1.1 milligrams per deciliter, compute beta, the probability of a type 2 error. So if you recall, when we were setting up the hypotheses, the alternative hypothesis had a not equal to symbol. So we didn't have a specific value of mu under the alternative hypotheses. Mu was anything but 1.0, but it doesn't specify a particular value. So, but in order to compute the probability of a type 1 error, we have to do a what if. Well, what if mu was 1.1? What would be the probability of a type 2 error? Or what if mu was 1.2? What is the probability of a type 2 error? So we're doing a what if here. We're going to compute, well, what if mu is actually 1.1? What would be the probability of a type 2 error? You may recall, according to the critical value method, of probability of type 2 error is the probability of that we don't reject H naught if HA is true. That's a type 2 error. So, and then if we look at the formula for when we fail to reject H naught, we fail to reject H naught if the test statistic is between the two critical values for the table. So for the error types, I think it's going to be easiest if we use the critical value formula, work from that formula. Okay, so the probability of type 2 error, beta, probability of fail to reject H naught if HA is true, the probability that the test statistic is between the two critical numbers from the Z table, and we can use the same critical numbers we used before. It was 1.96, and I'll put my pen here. So this is the probability of negative 1.96 less than x bar. Now x bar we're going to treat as a variable, and the mean under the null hypothesis was 1.0 or 1. Sample size was 40, and standard deviation of 0.5. If u equal 1.1. Okay, so we can compute square root of 40 divided by 0.5 on the calculator. That's a 12.6 something. So this is equal to the probability of negative 1.96 less than x bar minus 1 times the 12.6491164 less than 1.96, and that's if u is equal to 1.1. Okay, so so this is intermediate algebra. We want to solve for x bar, so we want to isolate the x bar. So we divide everything by the 12.96 something. I'll put 3 dots. I won't write out the whole thing. Just divide each piece by the 12.6 something. 12.6. And in the middle, it's going to cancel. So this will cancel, and then we can do the division. 1.96 divided by the 12.6 something, and we'll get a long string of decimals here, negative 0.15495 less than x bar minus 1.0 less than 0.15495 and a long string of decimals. And that's if u equals 1.1. Okay, so now again we're solving for x bar. We want to isolate the x bar. We can add 1 to all sides of the inequality, and then we'll get probability. Signs are different here, so you subtract. It'll be 0.85 something. Okay, so I'll put these in the calculator. So we have this okay, so we have the 1 point. I have these in memory already, so I'll be 1 plus a negative 0.15 something. So let's go 1 minus, second, recall, I get 0.845 something, a long string of decimals. and then the 1 plus the 1.49. Is going to be the 1.15, 495, 1605. And then it's if mu is equal to 1.1. Okay, so now we can make this into z-score by subtracting the mean divided by standard deviation. And we're assuming that mu is equal to 1.1. So here's where our assumption comes into play, that mu is equal to 1.1. So this is going to be probability of the 0.845, etc., minus the 1.1 times the square root of 40 divided by 0.5 less than z less than 1.15 something minus 1.1 times the square root of 40 divided by 0.5. Okay. Okay, so minus 1.1 equals times second square root of 40 equals divided by 0.5 equal. I get about negative 3.22. Less than z, less than, and this one here, okay, let's see if I have that in memory. Okay, this number here, the 1.15 something, minus 1.1 equals, divided by, 0.5 equals, second square root 40. I got approximately 0.70. Okay, so now we can look these up in the table. Go to row 3.2. If you're using a two-page table, you can go to row negative 3.2, but table in our book is a one-page table, so it only has the positive side, but the bell curve is symmetric, so we can use the symmetry. You look up both numbers. For z between a negative and a positive, we want to add the numbers from the table. And that's if you're using, assuming you're using the one-page table like the one in our book. There's also one in the course files too. Here's the one in the course file. So row 3.2, column 2. 3.2. Yeah. Well, you're not going to be able to see the column heading here, but this column 2 is the third column. The column there is 0, 1, and 2, so it'll be the third column. And row 3.2, and it's going to be, I have 0.4994. Okay. And then go to row 0.7, column 0, and that's 0.2580. Okay, so if we add these, 0.4994 plus 0.2580, 0.7574, or approximately 0.76. So this is higher than what we would probably like. That's a pretty high probability. If mu is actually equal to 1.1, we have it's more likely than not we're going to make a type 2 error here. 76% chance of making type 2 error if the actual population mean is 1.1. And we can, so it's a 76% chance of making a type 2 error. These numbers here on this step here, sometimes those are reported separately. Those are the critical values, critical X bar values. The book labels them X bar crit. If it's a two-sided test, you'll have two values. So this is a two-sided test. The one-sided test will have one critical value. If we go back to the original hypotheses, the original hypotheses had a not equal to symbol here. That's a two-sided test. If you have a greater than symbol, it'd be a right-tailed test, a less than symbol, a left-tailed test. But this is a two-sided test here. So we'll have two critical X values. And then we can also compute the power of the test. Power is 1 minus beta. That's going to be I have a page here. Power of test 1 minus beta. So it's going to be 1 minus approximately 1 minus 0.76, or about 0.24 would be our power. Okay, so that's not a particularly powerful test. If mu is actually equal to 1.1, there's only a 24% chance of making the correct conclusion to the test. Okay, so I want to talk a little bit about the the terminology of hypothesis testing. So in this part D here, take whether and what type of error and give the symbols for their probabilities. So I have four questions here, or four statements. If we conclude that the mean creatine level is different when it is actually the same as the general population, that's going to be an error, or our conclusion is different when it should be the same. And that's so if we go back to this chart here, we reject H naught. The same means H naught is true. Different HA is true. So this is the same and different. So if we reject H naught when H naught is true, that's a type 1 error, and its probability is alpha. I like to call that alpha the level of doubt, although it's also called the level of significance. So the answer to part 1, it's a type 1 error, alpha. The actual level of significance is, or level of doubt, is called the p-value. Alpha is the sort of maximum desired level of doubt, but the p-value would be the actual probability of a type 1 error. If we conclude that the patient creatine level is different when it is different, well, that's not an error. The conclusion is different, and it is different. Different is that's alternative. This is HA. A different difference is HA, and the same as HO. Okay. This is HA. Okay. So we don't reject H naught. That means we accept HA, and HA is true. So that's different. Okay, we reject H naught. I'm sorry. We reject H naught, and HA is true. So that means it's different. It's different. Okay. So that's going to be the power of the test, and that's not an error. That's 1 minus beta. So the answer is down here. It's the power of 1 minus beta. Fail to conclude that the patient creatine level is different. So this is and when it is different. So different means HA. And if we fail to reject H naught, that means we're you don't really accept H naught, but it's kind of almost like accepting H naught if you fail to reject H naught. So we don't reject H naught when HA is true. So that's going to be a type 2 error. That's going to be beta. And fail to conclude the patient creatine level is different when it's actually the same as that. So that would be not an error. That's going to be the 1 minus alpha. That's our confidence level. If we don't reject H naught when H naught is true. So it's we don't conclude it's different. That means it's almost like saying it's the same, although we never really accept H naught, but it's almost like accepting H naught if we don't reject it when H naught is true. The reason we never accept H naught is that because a lot of times these conclusions depend on the size of the sample, and it might be that a larger sample would provide stronger evidence of a difference. So we never really accept H naught technically, but sometimes the language gets a little awkward when you hit with the double negatives when you say you don't reject H naught. But so sometimes people will talk about accepting H naught, but technically it's we never accept H naught. But in example 2, now example 1, we assume that we knew the population standard deviation, but more typically, if you don't know the population mean, you're probably not going to know the population standard deviation either. So example 2 would be in some ways more realistic. We have a random sample of n equal 31 sedentary people. The mean glucose level x bar 5.1 milligram per deciliter with a sample standard deviation s equal 0.6 milligram per deciliter. The population mean creatine level u is unknown. Standard deviation sigma is unknown. And we want to compare this to the general population where the mean glucose level mu 0, 4.8 milligrams per deciliter, with standard deviation sigma 0.5 milligram per deciliter. We'd like 95% confidence, 5% doubt. So in symbols, we're testing H naught, mu equal 4.8 milligram per deciliter. Sedentary glucose is the same versus alternative HA, mu not equal to 4.8 milligram per deciliter. Sedentary glucose is different. Now the sample sedentary glucose was 5.1. That is different than 4.8, but that might have happened by chance. The question is whether how strong is the evidence that the population mean is actually different than that of the general population. Okay, so there's 3 methods we can do. We can do a confidence interval, and but when we set up the confidence interval, instead of looking in the z table, we're going to look in the t table, because the t table is it's another bell curve. Both z and t tables are bell curves, but for the t table, it's the bell is a little bit more spread out. There's more in the tail, and for large samples, the t table is pretty much the same as the z table, but for smaller samples, the bell is a little bit more spread out. So we're going to use the t-table here. And we want to look in row, for our t-score, look in row n minus 1, 31 minus 1, which is 30, and column alpha over 2, 0.05 over 2, or 0.025, to get the critical values. So pull up the t-table here. There's one of the course files, and there's also one in the book. I'll look in row 30. Here's row 30 and column 0.025. So I get 2.042. The critical values would be plus or minus 2.042. The margin of error would be t times s divided by square root of n. So it's going to be 2.042. S is 0.6, and n is 31. So it'll be 2.042 times 0.6 divided by second square root 31 equals 0.22 something. Okay, so the lower bound is going to be 5.1 minus the margin of error, which is about 4.88. Upper bound is 5.1 plus the margin of error, approximately 5.32. So that means we're 95% confident that the mean glucose level of sedentary people is between 4.88 and 5.32 milligrams per deciliter. And because the population, the general population mean glucose 4.8 is not between those two numbers, that means we can reject H0 with 95% confidence and conclude that the glucose level of sedentary people is different than that of the general population. Okay, so that's the confidence interval method. We can also do the critical value method. Again, we'll get the same critical values, plus or minus 2.042. The standard error of the mean, s divided by square root of n, is 0.6 divided by square root of 31. And that's going to be 0.6 divided by second square root 31, 0.1 something. I'll store that in memory. And then the test statistic with a z-score, or it's actually here a t-score, but it's sort of the same thing as the mean minus the sample mean minus the mean of the mean, if H0 is true, divided by the standard deviation. So it's 5.1 minus 4.8 minus 4.8 equals, divided by second recall, equals 2.78 something. Okay, so our test statistic is approximately 2.784. Is not between the two critical values of plus or minus 2.042. So that means we reject H0 with 95% confidence and conclude that the mean glucose level of sedentary people is different than that of the general population. Okay, so we can also do the p-value method. Now, p-value method is it's hard to compute an exact p-value from our tables, but we can maybe estimate it from the tables. With technology, today's technology, actually, you can just get it from a computer, but we can estimate it from the table here. Okay, so we can look in row n minus 1. 31 minus 1 was 30 of the t table, and actually, we don't even really need this. This is we need the we don't really need this step here. This is you need that for the critical value method, but you don't really need it for the p-value method. Standard error of the mean, s divided by square root of n, the same as we had before. It's 0.6 divided by square root of 31, and it's approximately 0.10763.181, and then compute the test statistic, same as we did before. 5.1 minus 4.8 equals divided by 0.107763.181, and it comes out to be approximately 2.784. And then we want to go to look for 2.784 in row 30 of the t table, and the closest t value there is 2.750. It's in column 0.005, and because it's a two-sided test, we wanted to multiply by 2 to get 0.001. Because 2.78 is slightly larger than 2.750, the p-value will be slightly less than 0.01. So let's go take a look at the t-table again. We're looking in row 30, and here's the closest p-value. It's 2.457. Let's see. No, it's 2.750. We have 2.78, and here we have 2.75. So that's going to be the closest one. That's in row 30, and the column is 0.005. And we want to multiply that by 2 because it's a two-sided test. So 2 times 0.005 is 0.01. And because our t-score is, our test statistic is slightly larger than the number in this table, that means the p-value is going to be slightly less than 0.01. Because 0.01 is less than 0.05, which is alpha, we again reject H0 with 95% confidence and conclude the mean creatine level of such patients is different than that of the general population. We can also go a little bit further than that. Because our p-value is less than 0.01, the sample provides strong evidence that the p-value is that the creatine level, glucose level of the sedentary people is different than that of the general population. If I can go back here, p-value less than 0.01 provides strong evidence. And we could, again, with technology, we can actually get a more precise p-value, but I'm not going to really emphasize that in this course. The technology that we're mostly using is the TI-30X2 calculator. Okay, so let's Okay, so we can also, with the same example, do a test for the variance. So we can test h naught sigma squared is equal to 0.5 squared. Secondary variance is the same, versus sigma squared not equal to 0.5 squared. Secondary variance is different from that of the general population. So the same example, except now we're testing the variance. And again, we can use the three methods: the confidence interval method 1. Our desired level of doubt is 0.05. 0.05 divided by 2 is 0.025. And then for we're going to be using the chi-square table, which is not symmetric. For the z and the t tables, those are bell curves. Those are symmetric, and we just have to look up one number in the table. But when we're testing the variances, we're going to be using the chi-square table, which is not symmetric, and we're going to have to get two numbers from the table. We're going to do 1 minus alpha over 2. We're going to do alpha over 2, which is 0.025, and we'll also look up 1 minus alpha over 2, which is 1 minus 0.025, which is 0.975. So we're going to look in row n minus 1, which is 30, and columns 0.025 and 0.975 of the chi-square table to get the critical values of 46.979 and 16.791. And then so that's the chi-square table. Let me pull up that table here. So that's row 30, and well, it's a little hard to see the column numbers, so you can't really. Column headings don't really fit on the page here, but those are the column headings. But we want the 0.975 column, which is the third column over from the left, and we want the 0.025 column, which is the third column from the right. So row 30 is right here. So it's a 16.791 and 46.979. Okay, so those are the two numbers from the chi-square table. The lower bound, n minus 1 times s squared divided by the 46.979, 0.1598, and the upper bound, this is by, look at the formula again. It should be s squared, should be 0.6 squared. There's a formula, this is the formula that we're using here. So for the competence interval, you should have an s squared there. So that was, s was 0.6. Example 2, let's see if I can find example 2. Example 2, yeah, s is 0.6. So example 2, s is 0.6. Sigma naught is 0.5. So this should be a 0.6 squared. And it's going to be 30 times 0.36 divided by 46.979, 0.22 something. And then the upper bound, 30 times 36 divided by 15.791, 0.64. Okay, so that means we're 95% confident that the sedentary glucose variance is between 0.22, let's say approximately 0.23 and 0.64, and because the population variance 0.25 is between those two numbers, that means we fail to reject H0. So the sample does not provide enough evidence. So that doesn't necessarily mean we accept H0. It just means that the sample does not provide enough evidence to say that there is a difference there. The sample variance is slightly different than the population variance, but that could have happened by chance. And if we take the square root of those numbers, we can actually get the sample confidence interval for this standard deviation. So square root of 0.229889951, 0.47 something. Be 0.479, and this one's going to be square root of 0.64320171.802. So and again, because 0.5 is between these two numbers, that means we fail to reject H0. Okay, we could also do the critical value method. Critical value method we're using this formula here, and we have the same numbers from the table. The test statistic is n minus 1 times s squared over sigma naught squared, so it's going to be approximately 43.2, and because 43.2 is between the two critical values, we again fail to reject H0. And it's the same test for if we're doing a standard deviation. P-value method, again, the test statistic is 43.2. We want to look in row 30 of the chi-square table, n minus 1 is 30. And the closest value is in column 0.05. And since we're doing a two-sided test, we multiply by 2 to get 0.1. And our test statistic is less than the number in the table, so our p-value is actually going to be more than 0.1. So again, we failed to reject H0, and the sample does not provide enough evidence. So if you look in the chi-square table in row 30, and we're looking for something close to 43.2 in row 30. So row 30 and 43.7 is the one that's closest. So if we go up to the column heading, it's 0.05, and then multiply by 2, we get 0.1. Okay, so and then so our p-value is going to be more than 0.1, so that means that the sample provides little evidence that the variance of the sedentary population is different than that of the general population. Okay, another example of hypothesis testing. A sample of n equal 90 patients, the proportion cured by new drug. P hat, 54 divided by 90 is 0.6. And want to compare it to the 0.47 proportion cured by the old drug with confidence level 1 minus alpha 97% and doubt 3%. In symbols, we're testing H naught, P equal 0.47, new drug is not better. In this case, we'll do a one-sided test, because really we want the, we could do either one, but it depends on how the problem is worded. But here they're asking for a right-tailed test. And that is fairly common if you're testing a new drug, because you only want to invest money in a new drug if it's better than the old one. You don't want to invest money if it's worse than the old drug. So it's common to do a two-sided test one-sided test in this situation. So the alternative here, P is greater than 0.47. The new drug is better than the old. So it's a right-tailed test because of the greater sign in HA. So we're just going to do, I think just we'll start with, we're going to skip the confidence interval here. We'll just do the critical value method and the p-value method. We want to check that n times p is 0. Actually, we want for the confidence interval method, we would check that n times p hat is at least 5 or more than 5. But for the critical value method, we want to check that n times p 0 is more than 5, and 90 times 0.47 is 42.3. That's more than 5. That's a yes. Q0 will be the proportion not cured by the drug. This is it's 1 minus 0.47 is 0.53. 90 times 0.53 is 47.7. That's also bigger than 5. So that means we can use normal approximation. Otherwise, we need to use binomial probabilities. And then because it's a one-sided confidence interval, we don't need to divide. We don't need to use 1 minus alpha over 2. We're just going to do 0.5 minus alpha. 0.5 minus 0.03 is 0.47. And we'll look in for 4700 in the body of the Z table. The closest values are 0.699 and 0.4706. If you look at the last digit here, we're looking for 47. It's going to be closer to the 4699. The last digit is off by 1 here. It's off by 6 there. I'm going to guesstimate it'll be something like 1.881. This number 0.4699 is in row 1.8. This one's in row 1.89. So it's going to be somewhere between 1.8 and 1.9, but closer to 1.88. So I'll say 1.881. And this is our upper critical value. And then to test statistic, 0.6 minus 0.47 p hat minus p0 times the square root of n divided by the square root of p0 times 1 minus p0, and that's equal to 0.6 minus 0.47 equals times second square root 90 equals divided by second square root 0.47 times 0.53 equals. It's about 2.471, and that's larger than our upper critical value of 1.881. So we reject H naught with 97% confidence and conclude the new drug is better than the old. Okay, so we can also do the p-value method, and the first two steps are going to be the same. The test statistic is going to be 2.4, approximately 2.47, and we want to look in row 2.4, column 7 of the Z table, and let's see what's in there. 2.4, column 7. Uh, 2.4, column 7. I get 0.4932. So it's going to be 0.5 minus 0.4932. It's about 0.0068. And this is a one-side test, so we don't have to multiply by 2. And 0.00 is less than 0.03. That's our value of alpha. So again, we reject H naught with 97% confidence, include the new drug is better than the old. And also, because our p-value is between 0.001 and 0.01, the sample provides strong evidence. Okay. Okay, so the next example is we have two samples. We have a sample of 17 smoking areas where the mean carbon monoxide level is 15 parts per million with a standard deviation of 8 parts per million. And we have a sample of N2 equal 11 non-smoking areas where the mean carbon monoxide level x2 bar is 7 parts per million with a standard deviation of 2 parts per million. And we're going to assume that the carbon monoxide levels are normally distributed. That means a bell-shaped graph. And we want confidence level 95% or a level of doubt 5%. Test H naught. CO levels are the same versus HA. mu1 not equal to mu2. CO levels are different in smoking versus non-smoking areas. So the first step is to compute the row of the t-table that we're going to use. This is probably the hardest step here. This is kind of a complicated formula here. This comes out to be 18.9 something, and we want to truncate this, so it's going to be 18 degrees of freedom, or row 18 of the t-table, and then we can compute the test statistic, the difference between the two means, divided by the square root of s1 squared divided by n1 plus s2 squared divided by n2. Plug in the numbers, it comes out to be about 3.937. And this is more than our okay, I skipped this step here. The critical value we get from looking in row 18, column alpha over 2 of the t-table, which is plus or minus 2.01. So our test statistic is more than our upper critical value of 2.101. So we reject H naught with 95% confidence and conclude the mean CO levels are different in smoking versus non-smoking areas. In fact, 3.937 is more than any of the values in row 18 of the t-table. So the p-value is going to be less than 0.002, which provides at least strong evidence. We can also test whether the variances are the same, and for this I use the F table, and we want to look in depending on the table, tables in the that are in the course files. This would be the first number would be the row group, and then this would be the page, and then the row and the column, so that gives the critical values are from the S table. And then for the test statistic, it's S1 squared divided by S2 squared, so it would be A squared divided by 2 squared, which is 16. Let's see, this table in the book is organized a little bit differently. Pull up that table here. So we're looking in row group 16. This would be the row 0.025, row group 16, and column 10. So that would be right here. We have row group 16, 0.025, row 0.025, column 10 is 2.99. I had my table, I got this number from my table, which is about the same. It's rounded off as about 2.99. And then that's the one in the course files, but the one in the book doesn't carry as many digits. And then the other one would be row 0.025, row group 10, column 16. So let's see if I can find that. Row 10. Row group 10, row 0.025, and column 16. Well, the closest one to 16 is 15, so it's could be somewhere around 3.52, maybe somewhere around 3.5. It's approximately 3.5, let's say, I think my table in the course files I got 3.49 something, but let's say approximately 3.5. The one on the left you have to divide by the number for the table. It comes out to be 0.33 approximately, and the one on the right you don't have to divide. But anyway, our test statistic is not between the two critical values, so we're pretty sure that the variances are different, and also we would reach the same conclusion for the standard deviations. Okay, here's a test for difference of proportions. We have a sample of N1 equal 80 patients with moderate symptoms. The proportion cured by the new drug P1 hat, 60 over 80 or 0.75, and random sample of N2 equal 40 patients with severe symptoms, proportion cured by the new drug P2 hat, 20 over 40.5. And we want 97% confidence, 3% doubt. We want to test P1 equal P2, cure rates are the same, versus P1 not equal to P2, cure rates are different, depending on the severity of the symptoms. And we'll just do the we'll start with the critical value method here. We'll skip the confidence interval. So we first check that each of the n's times each of the p's is bigger is at least 5, and that's true. That's going to be a yes. And then the next step is to compute the pooled sample proportion. So it's going to be n1, which is 80, times p1 hat, which is 0.75, plus n2, which is 40, p2 hat, which is 0.5, divided by n1 plus n2, which is 80 plus 40. So this comes out to be 60 plus 20 divided by 120. It's going to be about 0.66 in repeating sixes. Put a bar over the 6. Okay, and then our confidence level is 97%, divided by 2, 0.4850. We'll want to look for that in the body of the Z table. It's in row 2.1, column 7. So if we go to the Z table, we're using the table in reverse for much of the Z table here in this part of the course. We're mostly using it in reverse. So looking for 4850 in the body of the Z table. It's in row 2.1 and column 7. Okay, so so the critical values are plus or minus 2.17. Then we can compute the test statistic, P1 hat. So it's going to 0.75 minus 0.5 divided by square root the pooled sample proportion, which is 0.6 in repeating sixes, and 1 minus that is going to be 0.3 in repeating threes. I'm putting a bar over the 3. Square root of 1 over 80 plus 1 over 40. Okay, so so this comes out to be approximately 2.74. And the test statistics are the critical values are 2.17. So 2.74 is not not between the two critical values. So that means we reject H0 with 97% confidence, and conclude the cure rates of the new drug are different depending on the severity of the symptoms. And for the p-value method, it's a two-sided test. So we multiply by 2. We look in row 2.7, column 4. It's 0.4969. Subtract from 0.5, multiply by 2. We get a p-value of 0.0062. That's less than less than alpha. That can reject H0. Furthermore, it's between 0.001 and 0.01. So the sample provides strong evidence that the cure rates are different. And that concludes this presentation.